Hello students, welcome to EPG Pathshala. I am Dr. Imtiaz Hassan from Jamia Millia Islamia, a Central University. Today we are going to talk on module Basic Principle of CD Spectroscopy and Instrumentation under the paper Techniques Used in Molecular Biophysics 2. So after studying this module, a student will be able to understand what are the circularly polarized light, then physical principle of circular dichroism. Then you must know about the optical rotated dispersion, that's known as ORD, and comparison of the CD and ORD. Then we discuss about the instruments or components of the CD spectropolarimeter. Then we discuss about the information available from the CD studies of proteins, and at last we discuss some experimental condition and general consideration while using the CD spectroscopy. So let's give you the very important information about the circular dichroism. It is the simply measure the difference in the light absorbance between left polarized light and left circularly polarized light with the right circularly polarized light. And CT spectrometer, which is also known as, it's a kind of a spectrophotometer, is a specialized variant of the absorbance spectrophotometer which measures actually difference in the light between the left and right circularly polarized light. It is measured as a quantity called mean residual ellipticity, which is an indication of a structural content of any biomolecules. Generally, all optically active compounds exhibit CD in the region of appropriate absorption band. So, optically inactive molecule does not have show any CD. CD is measured as a quantity called mean residual ellipticity. Its unit it's represented in the unit, that's the degree centimeter square per decimole. And the absence of regular structure results a zero CD intensity, while an ordered structure results in a spectrum which can contain both positive and negative signal. So now we discuss about the types of polarized light. There are two types of polarized light. One is the plane polarized light, one is the circularly polarized light. A plane polarized light beam results from the sum of two-phase circularly polarized beam of opposite sign. So if the both left and right circularly polarized light are equal in a magnitude but equal opposite in direction, that leads to the formation of plane polarized light. However, a circularly polarized light beam results from the sum of two perpendicular plane polarized light beams dephased by 1/4 wavelength, or pi by half of the pi by 2, half of the pi. A plane polarized light beam of which one of the circular component left or right were differentially absorbed by dichroic sample would result an elliptically polarized light beam. And the differential absorption of clock and anti-clockwise component by an optically active compound results in a rotation of the plane in the light. We discuss about how to produce the linearly polarized light. You can see here the first is the unpolarized light, when the light is propagated in all the direction. However, the linearly polarized light which propagated in a linear direction, it is produced actually by it containing two vectors. One is the vertical polarized light and one is the horizontal polarized light. Both are having equal in amplitude and opposite in orientation, so it gives the linearly polarized light. We discuss how we produce circularly polarized light. You can see here there are two types of light. One is the left circularly polarized light, one is the right circularly polarized light. So the circularly polarized consists of two perpendicular electromagnetic plane waves of equal amplitude and 90-degree difference in the phase. That leads to the formation of circularly polarized light. The light illustrated is right circularly polarized light when it is directed towards the right side, while the other is the left circularly polarized light. We discussed that the differential absorption of two circularly polarized beam. You can see here that when both E left or E right are equal in magnitude, then it gives rise to the linearly polarized which can be viewed as a superimposition of opposite circularly polarized light with an equal amplitude and phase. In substances with optical activity, the left and right circularly polarized light beams are traveling at different speed and are absorbed to a different extent. The CD is characterized by the ratio of semi-minor and semi-major axis of the ellipse, which is given in the form of tan theta. It equals to C by B as shown in the figure here, and theta is known as the ellipticity. We discuss about the optical rotatory dispersion. It is defined as the angular velocity of the left and right circularly polarized beams are different in the sample. The orientation of ellipse alpha is called optical rotation. The measurement of optical rotation is dependence of the used wavelength is the optical rotatory dispersion. You can see here it having both positive and negative sign, while the CD is having either positive or either negative signature. We further explain the optical rotatory dispersion if the refractive indices of the sample of the left and right-handed polarized light are different. When the components are recombined, the plane polarized radiation will be rotated through an angle alpha. And N1 and N are the indices of the refraction of left and right-handed polarized light. And alpha is the radian per unit length from the lambda, and it is given as N1 minus Nr divided by lambda. And the optical rotation is defined as the radian per centimeter phi equals to pi by lambda into NL by Nr, where N is the refractive index, lambda is the wavelength of the light, and phi is the angle of rotation in optical rotatory dispersion. We discuss about the optical rotation. It is usually reported as a specific rotation alpha, which measures at a particular temperature, concentration and wavelength, normally 589 nanometer, and it is given as the molecular rotation phi is defined as alpha into mw into 10 power minus 2, where alpha is the 10 square alpha divided by LC, where C is in the gram per 100 ml and alpha is alpha by C prime D prime, where the concentration of an optically active substance C expressed in gram per centimeter, and D is the thickness of the sample in decimeter. So finally the M equals to M into alpha into 10 to the power minus 2 equals to M alpha into 10 to the power minus 2 divided by C prime D prime, where M is the molecular weight of the optically active component, and the 10 to the power minus 2 factor is subject to convention and is not always included in M. Now we discuss about the optical rotatory dispersion, that's ORD. The ORD curve is a plot of molar absorption, that's alpha or mole, versus the wavelength, and clockwise rotation is plotted positively. However, the counterclockwise rotation is plotted negatively. ORD is based solely on the index of diffraction. So-called plane curve is ORD for chiral compound that lacks a chromophore. Chiral compounds containing a chromophore can give anomalous or cotton effect curves. We discuss why is not chromophore is required in CD. So all chiral molecules exhibit circular birefringes, basically the rates of propagation of left and right-handed polarized light, which can be added to form a plane polarized light, are different. This changes their relative phase and therefore observed angle at the detector. With the background given so far, now we discuss the cotton effect. Positive cotton effect is where the peak is at higher wavelength than the trough, and the negative cotton effect is the opposite. So optically pure enantiomer always display opposite cotton effect in the ORD curve for identical magnitude. For if you have the left or right L or D configuration, they have showing the equal and opposite cotton effects. Zero crossover points between the peak and the trough closely correspond to the normal UV maximum, lambda max. And the different absorption of circularly polarized light changes its sign in the region of maximum absorption of ORD spectra are dispersive. However, the CD spectra are absorptive. We discuss about how the circularly polarized light are generated. You can see that the electromagnetic radiation, the one component starts with the half of the amplitude of the second component, and that's what it gives the circularly polarized light. Depending upon the location of lens, we can decide that whether it is the left circularly polarized light or it is the right circularly polarized light. Now we discuss about the basic concept of circular dichroism. It is simply the measurement of how an optically active compound absorbs right and left-handed circularly polarized light, and all optically active compound exhibits CD in a region with appropriate absorption band. CD is plotted as a E extinction coefficient left versus ellipticity of the left polarized light minus the right polarized light. That's represented in the delta E with respect to the wavelength and expressed in terms of alpha or phi. Then alpha is therefore an angle between the initial plane of the polarization and the major axis of the ellipse of the resultant transmitted light. The quantity phi is defined as such that the tan phi is the ratio of the major and minor axis of the ellipse of the transmitted light. Now we compare the CD with the ORD. CD plots are Gaussian. Rather than S-shaped for the ORD, and the positive or negative deflection depends on the sign of delta E or theta and correspond to the sign of the Cotton effect. How ORD spectra are dispersive, called a Cotton effect for a single band, whereas CD spectra are absorptive. The two phenomena are related by so-called Koenig-Kramer transforms. Maximum the CD occurs at the absorption lambda max, where more than one overlapping Cotton effects. The CD may be easier to interpret than the ORD with the overlapping S-shaped bands. We discuss about the CD instrumentation, which is the most important component of this module. You can see here that it having a large number of lenses, mirrors, and all are spaced in such a way that finally it produces circular dichroic signal. So you can see here that the plane polarized light is produced by passage of light from the light source through two prisms, prism 1 and prism 2, a series of mirror from M0 to M5 and slits S1 to S3. The ordinary ray O is focused by the lens L and passed through a filter F to the modulator CDM. The circularly polarized components are then passed through the shutter SH, you can see here in figure, to the sample compartment before the detection by the photomultiplier tube for the signal production. We discuss about the simple diagram of the CDS polarimeter. You can see here there is a xenon lamp which acts as a light source which emits the light of the 170 nanometer to 1000 nanometer wavelength. Then the light passes through the monochromator where we can select the light of a particular wavelength depending upon the requirement. Then it falls to the sample where the molecular absorption occurs, and then the signal is detected by the photomultiplier tube. In the ordinary absorbance, it is directly detected. However, in the circular dichroism, it is further logged in an amplifier, and then modular power supply give rise to the well-defined CD spectrum, which can used for the further analysis to understand the properties of the molecule under investigation. We discussed that how CD signal is generated, what are the mathematical calculation involved in a generation of the CD signal. So you can understand that if a plane polarized light falls on chiral substances, the radiation will be rotated through an angle alpha. which is given as alpha equals to n1 minus nr divided by lambda, where n1 and nr are the indices of reflection of the left-handed and right-handed polarized light, and alpha is in the radian per unit. So the rotation phi is given as pi by lambda in L minus Lr, where n is the refractive index and lambda is the wavelength of light and theta is the angle of rotation. Usually reported as a specific rotation alpha measured at a particular temperature concentration. So the molar rotation phi equals to alpha into mw into 10 power minus 2, or alpha equals to 10 to the power 2 alpha divided by LC, where L is the path length in centimeter and C is the gram per 100 ml, and alpha equals to alpha by C prime D prime, where the concentration of an optically active substance C is expressed in gram per centimeter and D is the thickness of sample in centimeter. So M equals to M alpha into 10 power minus 2 equals to M alpha 10 power minus 2 divided by C delta, where M is the molecular weight of the active substance and component of the 10 power minus 2 factor is subject to convention and not always included in M. We discuss about the physical principle of CD. In practice, CD spectroscopy is ellipticity determined from the difference in the absorption coefficient, that is theta lambda equals to constant EL minus ER into C into D, where D is the thickness and C is the concentration of sample. It means that the value of theta depends upon the concentration as well as path length. So a constant is actually 180 by 4 pi ln 10, which is generally equals to 33. So the molar ellipticity is given as mr theta by 10 dc, or it can be further expressed as theta lambda equals to 3300 E. E is the extinction coefficient. So the mr is the molecular mass in the gram per mole, and if the molar extinction coefficient of the left and right circularly polarized are known, the molar ellipticity can be expressed as the theta lambda equals to 33 into E. Delta A at particular wavelength equals to A of the left circularly polarized light minus A of the right circularly polarized light. So the difference in absorption between the left-handed and right-handed circularly polarized light is given as plotted as a function of wavelength in the form of CD spectrum. Now we discuss some common application of circular dichroism. It is most widely used for the protein and peptides to estimate the amount of secondary structure present. To estimation of the secondary structure, CD is most widely used techniques, and it also used to evaluate the conformational changes occur in a protein in any condition to different types of the molecular environment, change in the molecular environment. It also measures the ligand binding phenomena, the possibility to carry out both equilibrium and kinetic experiments. There are certain chromophore present in the CD molecule CD, which gives the near UV absorption band or the information on the tertiary structure of the protein. So these chromophores are aromatic side chains having pi to pi transition and absorbs nearly at 280 nanometer and used to investigate in the near UV region. So the phenylene, for example, showing maximum ellipticity at the 250 per mole per centimeter, and tyrosine is having 1000 per mole per centimeter, and tryptophan having 5000 per mole per centimeter, which this property is used for the estimation of tertiary structure of a protein. However, the backbone or amide bond is detected in the far UV region, where N to pi transition occurs approximately 210 to 220 nanometer. That's the major peak in the UV spectrum, and ellipticity value is around 100 per mole per centimeter. And for pi to pi transition, it is the 190 nanometer, and this information is used for the estimation of secondary structure content of a protein. In slide number 24, we discuss how the CD is used for the estimation of secondary structure of a protein. CD in the far UV region from 182 to 240 nanometer, where the peptide bond absorbs light and reports the overall content of the secondary structure. Here is a typical CD spectra of a protein which having completely alpha helical structure, which completely beta stranded and completely random coil. So if the value of purely alpha helical, purely beta stranded and purely random coil structure is known, as a can be taken as a reference to calculate the secondary structure of the protein, of unknown protein, their structure is you want to determine by comparing the spectra of all known values. Once you get the CD spectra, you need how to analyze and how you derive information from that spectra. So for that you must remember all these points. Like first, that all alpha helical peptide has an ellipticity of minus 38,000 degree per centimeter square per mole per residue at 222 nanometer, and all random polypeptide has an ellipticity of minus 1200 degree centimeter square per mole per residue at 222 nanometer. In general, the CD signal at 215 nanometer indicates the beta sheet content, and CD content at CD signal at 208 and 222 nanometer are used to estimate the alpha helical content of a protein. We discuss about the features of CD spectra. Like for the alpha helix secondary structure element, signal is positive, it gives pi to pi transition. Its position is between 190 to 195 nanometer. Molar ellipticity minima and maxima is ranges from 60,000 to 80,000, and its negative value is pi to pi transition, where position is the 208 and it's giving 36,000 plus minus 3,000, and in the negative value n to pi transition it at 222 nanometer, giving again minus 36,000 value and plus minus 3,000. For the beta sheet, the positive value indicates pi to pi transition, negative value indicates n to pi transition. The positive value lies between 195 to 200 nanometer and negative value lies between 215 to 220 nanometer. And it is ranges from the 30,000 to 50,000, and negative value ranges from minus 10,000 to minus 20,000. For the random coil, the negative value again indicates n to pi transition and positive value n to pi transition, approximately 200 nanometer for the negative signal, 220 nanometer for the positive signal, and its value lies in the 20,000. There are several online available tools which used to analyze the spectra, and based on the spectra analysis it will give you the information about the content of secondary structure. By that you can deconvolute or decompose the spectra and get the structural information. These are the well-known and famous tools online server used to estimate the secondary structure content in a protein, like SSE, known as secondary structure estimation, Contin, Baylock, Warslock-C, then self-consistence, Lincomb or CCA, then BPN, it is used based on the neuronal network method, SOM-BPN, and PROT-CD. We try to discuss how CD is used for the estimation of tertiary structure. The CD in the near UV region from 240 to 340 nanometer reveals the features of tertiary structure, that is the asymmetric component or fingerprint of the protein. You can see here the tertiary structure of some protein, and it also helps to determine the changes in the structure by changing the different concentration or atomic environment of the molecule. The signal obtained in 252 nanometer are due to the absorption dipole orientation and the nature of surrounding environment of the phenylalanine, tyrosine, cysteine, disulfide bond, and tryptophan amino acid. While using CD, we must be aware with the methods for the sample preparation, because if any error occurs during the sample preparation, it leads to the vague data formation, and that's what you are unable to get the actual information about the molecule which you are analyzing. So there are certain criteria which must be followed strictly like for the additive, buffers and stabilizing compounds. Any compound which absorbed in the region of 250 to 190 nanometer should be avoided, because in this region protein gives its own information. And a buffer or detergent or other chemical should not be used unless it can shown that the compound in question will not mask the protein signal. About protein solution, from the above follows that the protein solution should contain only chemicals which is necessary to maintain its structure and stability at the lowest concentration possible. You must avoid any chemical that is unnecessary for protein stability and solubility. The protein itself should be as pure as possible, and additional protein or polypeptide will also contribute for the signal, so it should be avoided. Contaminants, especially unfolded protein, peptide, particulate matter, that's like the scattering particles, anything that adds significant noise or artifacts in the signal contribution to the CD must be avoided. Filtering the solution with the 0.2 micron syringe filter is good enough to reduce the noise and improve the signal. For the data collection, it is the initial experiment are used to establish the best condition or for the real experiment. So for the best condition, it is generally recommended that the cells of 0.5 millimeter path length 0.5 millimeter path length should offer a good starting point because it's having the low noise. Then the protein concentration is generally 0.5 milligram per ml, and cell of path and the stabilizer such as metal ion should be minimum, and the buffer concentration should be 5 millimolar or low as possible to maintain still, so which can maintain the protein stability. We also must be aware that how to maintain this equipment, because any error in the maintenance, it also leads to a dramatic change in your spectrum. So before using this equipment, you must read manual carefully, and quartz cell are highly expensive. Handle it carefully and don't scratch or with the pipette. Quartz should be washed with the concentrated nitric acid for 1 minute, in bad case for 1 hour, followed by extensive washing with the distilled water, and then ethanol, followed by drying with the vacuum pump by blowing the nitrogen gas to them. And don't use pressurized air since it contains traces of the oil. Purge the instrument with the nitrogen before using. Oxygen will be converted by the UV to the aggressive ozone. That's what the nitrogen purging is essential. After switching on, allow the 30 minutes to warm up. Check the stability of the instrument by drift of the baseline, and regularly calibrate the equipment by using the calibrating agent. And lifetime of the light source is approximately 1000 hours. So don't keep these instrument on every time. You start the light only when you need it. We discuss about the various online tools available to predict the secondary structure content in a protein. Their spectra are taken. So first you take the spectra, and that spectra is further loaded to from this server. You can easily calculate the amount of secondary structure actually present. So the most common is the dichroweb. It is used for the analysis of protein CD spectra. It is available on the dichroweb server. Then another server is the PCDDB, again used for the protein CD data bank. Here it stores all the CD spectra of the well-known proteins. And the K2D2 server are used for the estimating secondary structure from the CD spectra. Another tool is Capito, which is also analyzing and plotting tools for the CD spectra. And CD Pro is used for the analyzing the CD spectra for determining the secondary structure fraction present in a protein. Their spectra has been taken. So students, let's now summarize what we have learned in this module. We discussed that CD signal are observed because of absorption band of the optically active compounds in the circularly polarized light. So only the optically active compound give the CD signal, and a chiral molecule doesn't give any CD signal. A CD signal can be positive or negative. It is depends on whether the left circularly polarized light is absorbed to greater extent than the right circularly polarized light, which giving the positive signal, or to the lesser extent CD signal is the negative. So it's totally depending upon the amount of light, amount of the left or right circularly polarized light absorbed. CD technique is mostly used for to estimate the secondary structure content of the protein, and also it is used for the, of course, tertiary structure estimation, but the secondary structure estimation is the very accurate. Moreover, it is used for the studying conformational transitions in the protein, like the changing from N state to D state, slight structural changes upon exposure to solvent, addition of any chemicals or denaturants causing structural changes. Then the whole protein folding studies is based on the application using CD. Then kinetics and cofactor binding to any protein is used to is estimated only by the CD spectrometry. The far UV CD in the region of 250 to 320 nanometer gives the important characteristic feature about the near UV CD gives you information about the tertiary structure of protein, and the far UV CD in spectrum give you the information about the secondary structure content. And CD can be used to observe how many secondary structural changes with environmental condition or interaction with the molecule. The near UV CD spectrum more than 250 nanometer of a protein provide information about the tertiary structure, localization of tryptophan, opening and closing of the structure, and a lot of feature whichever you can derive based on the chromophore of the protein. And finally, the CD is a particularly very powerful tool to follow the dynamic changes in the protein structure, which requires very low amount of protein and give you a lot of useful information about the protein structure, conformation and dynamics. Thank you very much.